works. Okay. All right. Yeah. Tough numbers to follow, so impressive numbers, but we're going to do it anyway. So I'm Tobias Menne from RWTH. This is Jan Heimann from University of Paderborn. And Tassos Alexandridis from Forth couldn't be here, unfortunately. But this is really a team effort, so 3 teams worked on that. And so we're going to basically present a few different front ends, 2 back ends, and the main focus of the paper is system combination. Our motivation was basically to combine multiple front ends, and we actually only looked on the real data in the development evaluation set. And like I said, this really was a strong team effort. And in that spirit, I would like to give to Jan to present the front ends.
Yeah, hello everyone. So I'm going to present our front ends and 1 back end. And the front ends are, well, kind of like, it seems like they are in the spirit of this competition, because everyone kind of switched to, well, doing basically the same. So what we use is one MVDR beamformer, which is similar to the one which was used in the previous challenge winner system from NTT. So we use complex Gaussian mixture models to basically get a mask estimation, and from that we estimate the spatial covariance matrices for noise and speech, at least for the 6-channel track. For the 2-channel track, we estimate only the speech mask, and use for the estimation of the covariance of the noise, we use the 400 or up to 800 milliseconds immediately in front of the utterance. And well, then the other front end is well, fairly straightforward superdirective beamformer, which estimates the TDOA based on what the baseline system provided. And for the noise, we assume that in this case it's spherically isotropic. And the last variation of the front end is the generalized eigenvalue beamformer. In this case, we use a neural network to estimate the mask for the speech and the noise, calculate the respective covariance matrices, and use these to calculate the steering vector with as a general by solving the generalized eigenvalue problem. So these are the front ends. So basically, for the 2 MVDR and GV, the idea is to estimate some mask, get the spatial covariance matrices, and use these to get a beamforming vector, which can then be used and just multiplied with the signal. So there's also 1 backend I want to present, which you may have seen in the poster session. So this is our what we call wide residual acoustic model. So it's based on a wide residual network as a kind of like extended feature extraction. So we feed in the F-bank features, and the deltas have like 3 wide residual blocks, and then we have a fairly basic like kind of classifier which uses 2 BLSTM layer and then 2 feed forward layers to get to the dimension of the number of state posteriors. And I will now hand over again.
Okay, so this is basically the training pipeline for our backend, which was the focus of our investigations for the system combination. So I think it's a fairly straightforward pipeline. In the first stage, we trained GMM, HMM on the clean data, or I would call it quasi-clean data. So it's the channel 0 of the real data and the Wall Street Journal data. And we used that to get the alignments for all the other channels and the process data. It was more a system design choice, because we trained a lot of systems and This just made it easier and faster to do that. We trained a speaker-independent acoustic model, so our acoustic models are 5-layer BLSTMs. The speaker-independent model was basically trained on channel 1 and 3 to 6, whereas the speaker-adapted model was trained on that data, plus some optional extension, which I will talk about later a little bit more. Also, the decoding pipeline, I would say, is pretty straightforward. Maybe one thing to mention is we did also an LM rescoring after the first pass recognition and used that for the speaker adaptation. Okay, so for the next 5 to 10 minutes, I'm basically going to throw some numbers at you. So hope that's okay. I want to give you an impression on what component basically yielded which benefit. So in the first line, you see the baseline system. So with our speaker-independent system, without rescoring, we almost already reached the baseline. So I'm basically always talking about the real evaluation set, by the way. If we do the rescoring, then we are already around 15% better than the baseline. Same is true for the speaker adaptation. If we do speaker adaptation plus rescoring, we already arrive at 6.8, which is around 40% above the baseline. Then, of course, since I said like one of our main objectives was to investigate different front ends, I want to show you the results of different front ends on the baseline backend and on our BLSTM backend. So here, those are the results I showed you before. So then if we replace the front end by the super directive beamformer, we are not really getting a significant improvement with the baseline backend. With our backend, there's a stronger improvement, still quite small. But also you see a difference between development real data and evaluation real data. This is also a theme that we saw constantly, basically. If we use the MVDR beamformer, we get already a pretty strong improvement on baseline backend and on our backend. So with that setup, we already beat the CHiME 3 best system, I guess. And if we use the best front end we had, which was the BLSTM supported GV beamformer, we arrive at around 4% word error rate. So then I shortly mentioned that we extended the training set. So what we did is we used channel 1 and 3 to 6, and then we added to the training set the processed training data, basically. And we wanted to see if that gives us some improvements, because it was often reported that it doesn't really help so much with retraining. So if we do it with a baseline beamformer, it doesn't really have a significant improvement, at least not on the evaluation set. Like I said before, it was a theme that we saw often, that on the real def set, it worked a little bit better than on the real evaluation set. Same is true for the super directive beamformer and the MVDR. I would say it gives a little better improvement, and surprisingly on the BLSTM supported GV beamformer, it then worked quite well. Unfortunately, and that's why it's gray, this system wasn't available to us at the submission. So this is basically just for complete overview. So then we wanted to do system combination. And even though the improvement by extending the training set wasn't that significant, we chose to use those systems. On the one hand, because on the development set, it actually worked okay. And on the other hand, because we wanted to have a bigger variation in the systems, which is supposedly good for system combination. So we did the system combination with a confusion network combination, and I'm going to show you the results. You can see the system weights and the results in those tables. So if we combine the two best systems by only using one backend, so we're basically only combining front ends here, we get an improvement from 4.0 to 3.5. Then adding the next system doesn't really give that much improvement, but the fourth system then again gives a little improvement to 3.4. So here you can basically see that every front end has a benefit in this kind of system combination. Then we had another backend, as Jan presented earlier. So now we have more variation, but this backend only was available to us with one front end. So let's see how that worked. So if we combine basically the best systems, which is here 3.48 and 4.0, we arrive at 3.1, which is already a nice improvement. Adding the next system brings us below 3%. Then the fourth system again gives us a small improvement. And interestingly here, the last system was optimized away basically by our algorithm. So we had a weight of 0 there. So our final result is 2.91. Oh, I forgot to mention that all those numbers, of course, are on 6-channel track. So we developed also our system basically on the 6-channel track. This was our main objective. And then we applied it to the other tracks, which looks something like that. So on the 2-channel track, we basically with the same systems, just applying in the evaluation phase the beamformers on 2 channels, we get a word error rate about 5.3. Yeah, and the 1-channel track, we basically just took both backends, didn't do any pre-processing, combined them. The combination gave an, yeah, I would call it insignificant improvement over the best system, but still a little bit better. So yeah, we arrived at 9.2 or 9.3. So then none of those systems were trained with sequence training. And as we all kind of know, sequence training always gives kind of a nice improvement. So after the submission deadline, we managed to also finish training that system. And I would like to show that those results as well, even though they are not part of the submission. But we basically trained system 4 with sequence training, and we were able to get an improvement from 4.0 to 3.4, which is a nice improvement. And if we replace that system in our system combination, we get from 2.9 to 2.7. So we're quite confident that we're not yet at the full potential of this approach. So we're planning to basically do the sequence training on all those systems, and we expect to get even nicer results there. That's our system, and I'm going to take questions from here, I guess.
So we have time for some questions.
So the laser baseline is already very good, but what are these mainly, like a BLSTM acoustic model, or are there some other special techniques inside in the BLSTM laser than the Caldi?
So in the BLSTM backend, I would say it's a pretty straightforward backend. So we did not apply any fancy techniques. I mean, we had some gradient noise, dropout, L2 regularization. So I mean, like, we basically threw everything at it that we have, but it's pretty standard techniques. So I would say there is nothing really special about that backend, except that it's a 5-layer BLSTM, which already worked quite well out of the box, I guess. So, by the way, we didn't use any of the baseline system software, so we no Caldi, and also only for the baseline beamformer we used the beamformer. Yeah.
Laser is better than Caldi.
I didn't say that, but it's yeah, of course. So it's not the same architecture. So that's not what I said. But Razor works quite well. Yeah.
Any other question? So actually, I have one question. So basically, you combine different beamformer. And I think in the way you implement the beamformer, you use different techniques to estimate the mask and also different types of beamformer. So I'm not sure if you had the time to look at that, but is it the mask estimation that plays a role, or using different types of beamformer when you combine the system? You have an idea which is effective?
Yeah, maybe. So I can answer that, at least for, well, using our backend. And what we saw is that we get using the same mask estimation, so the neural network to estimate the mask. If we use the GV beamformer and the MVDR beamformer, and look at the results, we get slightly worse results for the MVDR beamformer. But then if we analyze at which utterance yields which error rate, we see that is quite orthogonal actually. So it's like so at least in this case it was like the different beamformers and not the masking.
So you think that you could combine the same mask estimation, but then still combine the beamformer and get some gain?
Yeah, yes.
Okay. Thank you. So if there's no other question, you can thank the speaker. Any question? No? Okay, so let's thank the speaker.